Alright, so let's have a look at number 2. Number 2 proposes the cosine square function. There are many ways to do this. One way would be to use the chart, the famous ones that we've already derived, the Taylor expansions. Another way would be to use the famous method for finding any Taylor expansion that exists, and that would be using our super amazing key for the coefficients. I could do that. In this case, another thing that comes to mind is that you have a cosine square there. If you didn't have a cosine, it would be so simple because we already have the expression for cosine. But since you've got that cosine square, it's a little bothersome. But you could alleviate that because there's a famous power reducing identity that tells you that you can cosine square is equal to something else with no squares. In fact, I'm tempted just to do that because it would be so much easier. But in the spirit of sharing many ideas with you, I won't do it the easy way. Let me show you other alternatives. So here's one alternative. You have a cosine expression here. Let's use that one for my famous sheet. This is the cosine expression. One we've already derived, by the way. You shouldn't just be copying it down, not knowing where it came from. We took a lot of time to develop this idea of taking a function and expanding it into a polynomial. In any case, looks like this. Cosine of x, cosine of blah actually, would be the same thing as 1 minus blah square over 2 factorial plus blah to the 4th over 4 factorial, and so on and so forth. Right? So if I have a cosine of 4x, that would translate into plugging in 4x wherever I see the blah. So it would be 1 minus 4x quantity squared over 2 factorial plus 4x to the 4th over 4 factorial, and so on and so forth. Now all I gotta do is just square this. So cosine 4x times cosine 4x would be equal to 1 minus 4x squared over 2 factorial plus 4x to the 4 over 4 factorial, and so on and so forth, times itself. That is times 1 minus 4x squared over 2 factorial plus 4x to the 4th over 4 factorial, and so on and so forth. If you talk about foiling, this is like foiling, but foiling on a really big polynomial, infinitely long. But if you can get your hands around this, and you'll be set. It's easy to do. You just do small steps. Do the 1 first. 1 times everything. So that would be 1 minus 4x squared over 2 factorial plus 4x to the 4 over 4 factorial minus 4x to the 6th over 6 factorial, and so on and so forth. That's the one. And you've done that. Now do this one. So this one times that one would give you negative 4x squared over 2 factorial. That's the second term here times the first one there. Now I'm doing the second one times the second one there. That would give you 4x to the 4th. That's that times that over 2 factorial times 2 factorial. That's these ones. And then you do this one times that one. That would give you negative 4x to the 6th, because I have 4 here and I have 6 there, over 2 factorial times 4 factorial. And so on and so forth. And you would add these all together. Okay? And once you add these, you get 1 minus, I know the first 2 terms. To get the first 3 terms, you'd have to add another row here. The first one would give you 1 minus 2 of these, which would be 4x squared over 2 factorial times 2. Okay? And for the next one, you'd get that plus that, and then plus some other things. This would be one way to approach the problem. And it might already be enough to see some of these are true or not. So, and really that might be enough to figure out which one of these is a good candidate. I could take this one for example. To finish this, you'd have to add more rows here, infinite many foiling sort of, to get a more complete expansion. But even this part that we've done so far might be enough to rule out some of these choices. For example here, if you do, let's do with a different coloring. If you do this, this would be 1/2, and if you plug in n is equal to 0 here, for n is equal to 0, you'd get the first term would be 1's on the top, so it'd be 1 on the top and 1 on the bottom. And then for n is equal to 1, whatever, already you can rule out that a doesn't look good, because the constant term would be a half plus 1, which would be 3 halves. My constant here is not 3 halves, therefore I can rule out that one, and so on and so forth. Maybe you can rule out even this one here, or this one. You just have to plug in numbers. So let's try this one. 1/2 times, when you plug in n is equal to 1, this one starts off at 1. You get, in fact, -1 times 8 to the 2 times x squared all over 2. And so that's your first term. Your first term turns out to be not a constant, so already I can rule out this one. So this is the only one that seems promising. And so you check the first few terms and you can get it that way. Okay, fine, I'll let you do that, but let me give you another idea, another possible way to do it. So we have this famous idea that says that cosine square of x is equal to 1 plus cosine 2x all over 2, yes? I remember this because this is the famous one. This is how we integrate cosine square in Calc 1 in the first semester. Super famous formula. So that would tell you that cosine square of blah is equal to 1/2 plus 1/2 cosine of 2 times the blah. Now I've got a perfect expansion for cosine already. So here's my expansion for cosine. So I'm going to apply that. So cosine square blah is equal to 1/2 plus 1/2. And here I'm going to go fancy on you now. Usually I put it onto this formula. Now you can use this one as well. So it would be the summation of -1 to the n times twice blah raised to the 2n all over 2n factorial. Okay, that's what cosine of x is equal to all this, and then this expansion I can get it from here. All I did is replace x with 2 triangle, and so now I can say, well, what's cosine of square of 4x? Well, that would be 1/2 plus 1/2 times the summation from -1 to the n. I'm replacing 4x wherever I see a triangle, so this would be 2 times 4x. That would be 8x raised to the 2n all over 2n factorial. And now you see clearly that's equal to this one. Whoa, what an elegant way to do it, huh? Nice. Alright, that's 2 down. 38 more to go.